Hi everyone, in this video I'm going to cover the final lesson for chapter 7. We are going to look at connections to discrete random variables. So we're going to go back to things we learned in chapter 4 regarding the binomial and hypergeometric distribution, and we're going to compare them to the normal distribution. Now, before we begin, let's look at a short investigation. We're going to go back to chapter 4 and we're going to look at an example of a binomial distribution. A regular coin is flipped multiple times. Show the probability distribution for the number of heads as a histogram when it is flipped. Now, if you've forgotten, this is an example of a binomial distribution. Binomial distributions are characterized by independent events in which we have two probabilities, success or failure. In this case, the probability of success is 0.5. We have a 50% chance of getting heads. Probability of getting a failure is also 0.5. Now, our random variable x would be the number of successes. And we are going to have different experiments where we have different numbers of trials. So, what would happen if n was equal to 6? If we flip the coin 6 times. Now, remember the formula. For 0 successes, it would be 620 times 0.5 p to the power of n times q, which is also 0.5, to the power of n minus x. In this case, it's 0. Okay. Now, if we were to do that and try it for 620 for 0 successes, 621 for 1 success, 622 for 2 successes, etc., etc., we should get a probability histogram that looks a little something like this. Okay. Now, what if we were to do it 15 times? We had 15 trials. We can count the probability of 0 successes, 1 success, 2 successes, 3 successes, etc., etc. We are going to get a probability histogram that looks like this. Now, what if we had even more trials? What if we did this 50 times? What if n was equal to 50? We had a probability of 0 successes, 1 success, 2 successes, all the way up to 50 successes. It is going to look a little something like this. So, what do we notice about the shape of the probability histogram? And what kind of shape is it approaching? If we were to connect the midpoints, and this is a very rough drawing. Okay. Kind of like the frequency polygon. We can see that it is getting closer and closer to looking like a normal distribution curve, the bell curve. So what does this mean? For a certain number of trials, we can get a good estimate of the probabilities for a binomial distribution, and this also applies for the hypergeometric distribution if we have a large enough number of trials. And if the probabilities of a success or failure are within a certain range, and we have a certain number of trials, then we can model it using the normal distribution. This helps us quickly calculate probabilities for many possible numbers of successes. Because if we do it by hand to calculate the exact probability for the binomial hypergeometric distribution, it would take a lot longer. So we can approximate the answer using the normal distribution. Now, let's go through some formulas. Okay, so we just established as the number of trials increases for a binomial distribution, the closer it will approximate a normal distribution. Now, we need a couple of things first. We need the mean and standard deviation of a binomial distribution. That is found with NP. NP is the mean for a binomial distribution, and the standard deviation would be the square root of NPQ. Now, once again, remember n is the number of trials, p is the probability of a success, and q is the probability of a failure. Now we're going to need to use these formulas because, again, to calculate probabilities with normal distribution, we need the mean and standard deviation to calculate the z-scores. Okay, so let's look at a quick example before we start calculating probabilities. Let's look at an example where the probability of rolling a 6 on a weighted die is 0.25. So there's a 25% chance that this die will land on a 6. The die is rolled 25 times. Is it reasonable to approximate this distribution with a normal distribution? Give reasons for your answer. Okay, now to approximate it, there's two criteria. NP has to be greater than 5 and NQ has to be greater than 5. So we need a large enough number of trials, and P and Q need to be large enough so that NP and NQ are both greater than 5. Otherwise, the probability distribution will not look close enough to a normal distribution. We won't get a very good estimate. So in this case, what do we notice here? N is 25, right? This is our N, okay, the number of trials. The probability of success is 0.25. The probability of failure is 1 minus the probability of success, which is 0.75. So we get NP and NQ. We notice they're both over 5. So that means we can get a good estimate with the normal distribution. And what is the mean and standard deviation here? Just plug numbers into the formula. Okay. The mean is NP, which is 6.25, and the standard deviation is the square root of NPQ, which gives me approximately 2.17. All right, so when we use the normal approximation, when we use the normal distribution to approximate the binomial distribution, or later on the hypergeometric distribution, we need to apply something called a continuity correction. Now, what this is saying is that the number, okay, for a discrete random variable, if you remember from chapter 4, it lies in the middle of the bar of the histogram. So, for example, the value 3 is a bar that's between 2.5 and 3.5. So what does this mean? If we want to find the probability of, say, rolling a 6, 6 would be a bar that is between 5.5 and 6.5. Okay? So to calculate the probability of rolling a 6 exactly 3 times, sorry, I made a mistake. Our frequency, it should be 3. This should be our x here. So 3, 2.5, and 3.5 is what 3 is in between. Okay? So we need to calculate this bar right here. So we have to get the probability of x being in between 2.5 and 3.5 using the z-score table. To find a probability of rolling a 6 at least 3 times, at least means x is greater than or equal to 3. Okay? So if we're including 3, then that means we're starting at 2.5. Okay? So we calculate the probability of x being greater than or equal to 2.5. Again, getting the z-score and then finding the probability from the z-score table. To find a probability of rolling a 6 more than 3 times, okay, more than 3 times means it doesn't include 3. So we start here and then we move forward. So we calculate the probability of x being greater than or equal to 3.5. All right, let's do an example to illustrate this. Okay, we have example 2. A special coin has a probability of 40% for landing on heads and 60% for landing on tails. The coin is flipped 13 times. Using a normal approximation, find a probability of land on heads fewer than 4 times, exactly 4 times, and at least 4 times. First off, we have to determine whether we can use a normal approximation to get a good estimate. Remember, NP and NQ have to both be greater than 5. So NP here is 13 times 0.4, which gives me 5.2. NQ would be 13 times 0.6, which should give me 7.8. Okay, so NP and NQ are both greater than 5, so we should get a good estimate. Now, the next step, okay, so the first step is to check check to see if it meets the requirements for a normal approximation. The second step is to get the mean and standard deviation. The mean is NP and the standard deviation is the square root of NPQ. All right, now that we have these, we can calculate the probabilities. Fewer than 4 times. So fewer than 4 times means 3 times or less, right? So we are trying to, so imagine that we have kind of like something close to a bell curve, a normal distribution curve, like so. Okay, we want to find this whole area right here. Okay, and we can do that. Fewer than 4 times means an x value of 3.5 or less. Okay, so we're going to get the z-score for 3.5, which is negative 0.96, and get the probability of a z-score less than negative 0.96 from the z-score table, which is 0.1684. So there's about a 16.84% chance that you're going to land on heads fewer than 4 times with this special die, sorry, special coin. All right, exactly 4 times. Exactly 4 times is, we're trying to get this bar right here. So that's 3.5 and 4.5. We want to get the z-score for 4.5 and 3.5 and get the probability that'll be in between those two. Okay, so we already have the z-score for 3.5 from question A. For 4.5, the z-score is negative 0.4. So we want the probability of a z-score between negative 0.96 and negative 0.4. So we're going to subtract the probabilities from the z-score table. Okay, and that'll give us 0.1762. So there's about a 17.62% chance there. Okay, lastly, at least 4 times. At least 4 times means this whole area right here. Okay, so at least 4 times means we start at 4.5. Right? What we can do is, we already got the z-score for 4.5 from question B, so that's negative 0.96. So it's just 1 minus the probability of a z-score less than negative 0.96, which we get from the z-score table, and that is 0.8316. Okay, now we can also do the same thing for the hypergeometric distribution. If, just a quick recap, hypergeometric distributions are similar. The main difference between that and the binomial distribution is that we have dependent events. So remember, for the binomial distribution, our examples included flipping a coin, or spinning a spinner multiple times. Okay, a hypergeometric distribution would be, for example, taking things out of the bag without replacement, or being dealt a hand of cards. Those are examples of hypergeometric distribution. Now, the requirement here is the sample size needs to be less than 1/10 of the population. Okay, so if we're taking, say, 5 or fewer cards for a hand from a deck of cards, that'll work. Okay, the mean and standard deviation. The mean is the same as the binomial distribution, it's just NP. The standard deviation is the square root of NPQ, but we also have to multiply by the population minus the sample size over the population minus 1. Okay, so there's a slight difference there. So good example, Allison has a drawer full of unmatched socks. The drawer contains 30 blue socks, 30 green socks, and 30 yellow socks. She pulls socks from the drawer and records the number of blue socks in the sample. So, is it normal to approximate this distribution of a normal distribution? So we are getting, so 1/10 of the population is 9 because there are 30, 30, 30, 90 socks in total. N is 7 because we're taking 7 socks. Okay, this is our N. So N is less than 1/10 of the population. Okay, so that works. So that is the main requirement. So let's get some, or let's just jump to B now. Determine the mean and standard deviation of the normal approximation. The mean is the same thing as with the binomial distribution. It's NP. It's 2.33 approximately. The standard deviation, okay, N is 7. P is 1 over 3 because 30 of the 90 socks are blue. Q is 2 over 3, which is 1 minus P. So plug those numbers in to get the standard deviation. The population is 90, and we get approximately 1.20. What's the probability that 3, 4, or 5 of the socks are blue? So remember, if we're starting at 3, 3 starts at 2.5. Okay, 5 ends at 5.5. So we want z-scores for 5.5 and 2.5, and then we're just going to use the z-score table to get the probabilities for both and subtract them. So there's about a 44.02% chance that 3, 4, or 5 of the socks are blue. Now remember, you can always verify these answers kind of by using the actual formulas for the binomial and hypergeometric distributions. That can help you determine to see if your normal approximation is done correctly. Okay, that's pretty much it. So the main takeaway here, we can approximate binomial and hypergeometric distributions using the normal distribution. There is requirements to check to see if you can get a good approximation. You should do those first. Then you have to get the mean and standard deviation. Then you have to use the data values to calculate probabilities. Remember to do the continuity correction. Okay, any discrete data value is in the middle of the bar of the histogram. So it starts at 0.5 less and it ends at 0.5 more. Okay, so make sure you do that correctly when you calculate the probabilities. That's pretty much it. These are the practice questions you can try out before you do the textbook questions. Okay, please let me know if you have any questions. That concludes today's lesson.